you not sleep. Okay, so please try not to sleep. So there are two of us who will be doing the presentation. I am Santanu and he is Phaneesh. So we work in the digital section of Flipkart. I am not aware, for those of you who are from outside of Flipkart, whether you have ever used the digital downloads part of Flipkart. We offer MP3s and eBooks currently for digital downloads using apps, and MP3s are also available on PCs and other platforms. So basically what our team does is we are in charge of getting all the digital content, processing it, and finally delivering it to the end customer. So does anyone here have some idea about what kind of physical storage we have as warehouse for the physical goods? Okay, it's around 300,000 square feet. Okay, so what we'll be trying to do is, in this course of the next 20 minutes, we'll try to embark on a journey to try to build the warehouse for storing our digital content. So yeah, we tried consulting Dilbert's company to do that. Okay, let me tell you, it did not go well. So yeah, now moving on to the serious stuff, basically. What are the problems in a digital storage system, especially for storing digital content? First is the variance of file size. Okay, so we get covers of ebooks and album art with our music. Okay, those are a few kilobytes. We get ebooks which are about 800 megabytes. There are some books which are 700-800 megabytes. Okay, we have other data which can range to multiple gigabytes, say 30 or 40 gigabytes. Okay, so actually there is a huge variance between the minimum and the maximum possible file size of the that can go into the system. Second point is that there are so as I said, introspecting on what I said earlier, that we are concerned with processing and delivery of the content. So processing has one kind of requirement. Obviously in a processing system you would want very high and very parallel writes. That is the requirement in a processing system. On the delivery, you need massively fast reads and very scalable system which can serve lots of content at the same time. Again, another important feature that will come into picture is cost. Okay, because the content that may come in will be large. Okay, there will be millions of songs, there will be millions of books, and if we go into other verticals in the digital space, there will be lots and lots of content over there. Now, thing is, do we want the same behavior from all the content? As in, there will be some songs which will not get downloaded frequently after, say, 1 year after they are released. Do we still keep it in the highly parallel and very fast storage, or do we move it to some place where it's actually cheaper to keep them, and the only SLA we require is that we'll get the content back in a logical amount of time? Okay, so cost is another variable in the storage system. Besides this, so that goes about the physical storage part, behaviors that we need from the physical storage part. Besides that, what there is a lot of metadata management that we need to do to maintain sanity of the data first, and secondly to do lots of different kinds of queries on the system and to be able to undo some mistakes. So basically what we are looking at are version control on the files that goes into the storage, and lifecycle management, as in what is the state of a system. Is it just downloaded and not processed? Then we keep it at some place. Is it processed and ready to be delivered? Then we keep it in some other place. Okay, so that is a kind of lifecycle management that we would want from the system. Again, there may be something called variants of a content. Okay, as in variants are, let's say you have a song, you can have a FLAC version of that, you can have a 320 kbps MP3 version, and ranging down to, let's say, 64 kbps MP3. But they need to be clustered together so that it's easy for the user to switch between the different variants as and when required. So that is again not a part of the backend storage, but this clubbing will happen at some part in the metadata level. Okay. So it's a kind of metadata requirement that we have. So other points are, the other attributes that we would look from the system are, like, we'd want easy administrability on the system. We should be able to like take nodes in and out of the system and stuff. We want to cater to different kind of QoS characteristics, as in this song is supposed to be very, very popular in the next few months. Move it to some storage which is like, let's say, completely memory based. Okay, keep it in memory all the time. Okay, so that is some kind of QoS that we need to get. Metadata management and versioning I already told you. And we also need some self-healing capability, like high availability from our system, so that this is our warehouse, right? And we just cannot afford to tell users, okay, we will not be able to download the song for the, let's say, for the next 1 hour. Okay, it's just not done. So we need HA on the system. And we need concurrent reads. I think all of us understand that, like concurrent reads and concurrent writes on the system. And we would also want some kind of adaptive read-write system. As I said, that during processing we want more writes, during delivery we want more reads. Okay. So these are the different characteristics that we will be looking for in the system that we try to build. So currently, this is the system, sort of very high level view of the system that we are running, that's in service. We have a Solaris box with very high amount of storage with 16 RAID zones, okay, which runs ZFS. And the storage is mounted using NFS onto the client machines, which are, say, doing the delivery or doing the processing. And there is a separate metadata server and a metadata service that takes care of the versioning life cycle and variant tracking feature. Okay, so actually this is serving us quite well, but again we are looking at rapid growth in this segment, as in we may get more content and we have to be ready for that. Okay, so being ready for that means we have to identify and fix whatever problems we are getting from this system. So let's introspect a little bit about what are the issues that may come up. First is, foremost point that I can see is obviously HA. Okay, high availability of the system. It's a very, very resilient, very high-end box for the storage, but again, it's still one box. And if that goes down for some electrical fault or some other reason, then there may be some issues with delivery. Okay. Another problem is that currently the backend storage service is highly coupled with the clients. Okay. So even if we replicate the backend storage part, since the clients are doing NFS mounts over that, it will be difficult for the clients to switch from one box to another without doing explicit remounts. Another problem that may come up with the system is capacity scaling. Okay, so we have more than 100 hard drives on that system, but frankly adding any more hard drives will become a physical problem, as it's a physical chassis that will hold the whole system. Okay, so with this I actually pass the baton to Phaneesh, who will take you through what the architecture of the system that we are looking forward to.
Thanks, Santanu. So, Santanu kind of gave an overview of what we have currently. The major problem areas that we solved, if you look at the previous slides, which had the real problem areas where there is metadata tracking problems and tools problem that we have over distributed storage systems these days, and the solution that we have currently in production, which powers the digital store for Flipkart. But as Santanu was saying, we have identified problems, and we are working towards improvising or evolving the system towards a storage platform rather than just being a system implementation for a particular need, because we frankly we do not know what the need might be a couple of years down the lane. What we have what we are trying to solve here is all the shortcomings of the current implementation, as well as add some amount of adaptability and flexibility in the framework so that we can incorporate future needs, whatever it might be. So the metadata servers still do exist. So they are the main main infrastructure piece that actually solves most of the problems in a distributed computing environment. Better metadata management gives you better visibility towards your infrastructure, so you can have better tooling and better services. So we still have that, and what we are bringing in to solve the shortcomings is bring in a discovery service which talks to your storage infrastructure, or storage infrastructure has the software abstraction layers running, which will broadcast the capabilities in terms of capacity, performance characteristics, and availability to the discovery service. And as you can see, the clients are now decoupled from the storage infrastructure itself. There are no more NFS mounts. There will be again API abstraction on top of that, which will actually provide very transparent access to an appropriate endpoint. So if you look at the metadata service, it has another added element, which is the QoS, because as Santanu explained, different applications require different performance characteristics and availability characteristics. When in the data processing pipeline, say you are processing a 100 gigabyte log file and you are storing it somewhere, you would actually have to read it really fast and then process it. Now with the current setup, we can possibly optimize the hardware for reads by allocating more file memory, file system memory in the operating system, but that's one configuration that you can affect at that point in time. Say there is another application which is using the same service, which is writing or encoding music files. Now affecting a write optimized configuration on the same box, I don't think it would work, because most of the times these kind of configurations would warrant a reboot because it's an operating system configuration, etc. So you can actually have one characteristics at any point in time. So but when there are multiple clients, multiple applications, and multiple say QoS requirements, you cannot have just one hardware or one topology and expect it to perform at every use case. So even in the previous talks, many speakers mentioned this, it's access patterns. So you need to see how application is accessing certain things and what are the requirements. So with each request, you can set up QoS profile and say, you know what, I want 80-20 read-write ratio. So reads will be faster, writes will be slower. That's fine for me. Or you can say, 80, I want more writes. I don't care about reads because I'm writing to disk right now. So when you're doing that, most of the times, the QoS is set on write operations, which affects the file system or affects the content. So when you set it, the service, discovery service, and elects an appropriate hardware instance in your infrastructure, and then hands over handle endpoint to your client, which can actually perform that request. So get service. So say for example, you want to write a gigabyte file, and you said, you know what, I'm writing I really want it to be really, really fast. It's just like setting IO ops on EBS, volumes on your Amazon services. So you just say, I want these many number of writes, or you want a read-write ratio. And then metadata server will query and then hand over the handle to an appropriate instance. And we are front-ending this whole infrastructure, not just a service instance that is running with a read cache. So that, as Santanu was saying, it's an LRU cache. So you might have to keep the cache hot with files that are getting frequently accessed for reads. So the clients will get transparent access to the cache through the read APIs. So it will read through the cache, or if there is a cache miss, the meta service will give a callback to the cache handler to load that file from wherever it is available. So what we are doing now is we are partitioning the entire topology or the infrastructure that you have, which is optimized for a particular usage pattern that your client applications or clients might need. So this is where we are evolving towards. And I'll just take you through the call flow again. But there is metadata, and metadata management, and there is infrastructure management. There are two separate things here. So how everything works together? You make a call to the storage API, and storage API is talking to a metadata repository, which is highly available because just think of this as the name node in the Hadoop ecosystem if you are familiar about Hadoop. So, but it's more say flexible than the name node because we are using very different technology sets here. Unlike the name node, it doesn't have any memory restriction on, you can only have so many things at any point in time, and if you run out of memory capacity, you cannot have anything more. We are using different technology stacks there, and once you kind of make a call, say it's a write call, you're writing a file, so and you say I want an X to Z read-write ratio. So storage service will query the discovery service, and discovery service already has the metadata of your infrastructure, and say it returns a couple of service instances. Says, what, these services can service this particular request according to the QoS parameters that you are saying. And if there are multiple instances, there is leader election done, and just like Zookeeper, and it is just handed over an instance, the client gets a handle which actually is appropriate at that point in time. So, and then the client uses the HTTP write API and does the actual IO with the infrastructure. So still it is very transparent, and metadata is tracked on the storage API, which says, this particular request got processed and these QoS parameters were applied, and this is where it is stored in your storage infrastructure. So what we are providing is a location transparency to the clients. So the client need not know where the file was actually stored. So because when the same client or a different client tries to read, it's a named object, so he calls it by name, and the metadata server will resolve using the metadata and hands over the handle where that particular file or content is available at that point in time. So it's location transparent. It's location transparent to the clients. So that particular metadata is maintained on the repository itself. And say another client tries to write the same file, there is versioning. So it gets automatically versioned. That means at any point in time you can go back to a previously same state if your data processing pipeline screws up something. So that usually happens in the digital content space when you have a lot of media formats, and the content provider gave you a wrong format, or he gave you a corrupt file, and the previous version of the file that you had was somewhat better than this, but you screwed it up now. So you can actually affect rollbacks just by calling an API. You need not even go and use a tool. You just have to use a different version. So because this information is passed along with the packaging in the catalog, so you can just affect a different version in the catalog, and a different version will be downloaded when somebody requests for that particular file. So this is what we have on the call flow. So I think yeah. So another thing that we are trying to solve as a shortcoming is variety. So as Santanu was saying, it's a very, very high-end box. It's very resilient, and the file system that we are running has actually no history of total failures. ZFS has never known to fail completely, because the very reason why Sun built ZFS is to have data integrity and data recoverability 100%, and we have more than 100 drives across 16 different RAID zones, and it's replicated, striped. So it's very, very rare for any of the, like, colliding RAID zones to fail and data is permanently lost or becomes inaccessible. But as Santanu said, it's one electronic device, huge box, huge chassis with 100 odd drives. What if there is a power failure? What if there is a communications failure with the chassis itself? Because this chassis is connected to a very high-end server. There is a communications link, fiber optics link. What if that's at fault? So there are several failure points here. So what we are, and failures cannot be localized now. It's total failure. If there is communication breakdown from your box and the storage chassis, it's total failure. Data is still there, it's not lost, but you cannot access it anymore. So we are trying to localize failures and probably make the failures a little bit smaller, not catastrophic or total. So by having commodity boxes. So what we are saying is, it's just like in Hadoop world where you do not actually put loads of RAM, like loads of CPU if you do not have compute requirements. If you are using Hadoop just as a storage, HDFS as just a storage network, you do not need a high-end machine to, or high-end compute machines to, be in your hardware topology. So we are saying it's just very commodity boxes, but with lots of storage. Commodity storage again, just serial 88 drives connected, no RAID whatsoever, because what we are relying on is again distributed file systems like HDFS or other candidates that we are experimenting on, which can run off this and provide all the benefits of hardware-based, failover or resilient solutions. Huh? Right now we have at 2 different sites. Okay, so yeah, we'll actually talk about that in this slide, how we are planning. So what we are saying is, it's what the kind of underlying infrastructure software that we are planning to run, they are proven at scale as well as proven for resilience. So if you look at, say for example, the candidates that we are looking at in our lab, which we are experimenting on, GlusterFS supports replication, and it supports geography-based very intelligent replication over cross data centers. So we can configure that, and it's not like real time, but it's very near real time, and it's very, very intelligent. And because you can actually configure various partitions in your network or storage network to behave differently. You can only have certain parts or certain say instances in your say GlusterFS cluster to replicate across the data center. Say your data processing pipeline is using, say, a set of 11 nodes, and your delivery network is using, say, 30. You can say, I don't care about the data processing thing because I can always rerun them. I don't care about its high availability across data centers when something goes wrong in this data center. I want to replicate only that partition in the network. You can do that. So the underlying DFS is what is providing us all those capabilities across data centers, like replication, failover, adding capacity, replacing nodes when a node goes down, etc. So we are relying on the underlying DFS implementations, and the kind of subject, at least standards that we are looking at is GlusterFS and Ceph, which we are like running a lot of tests on to see how resilient they are, and to understand or to kind of at least capture all the performance and behavior characteristics in different configuration modes. So I think I answered that, but if
So you were using NFS mounts, right? And you removed that part now.
Mhm.
So GlusterFS provides a native cluster mount,
correct.
which can be used, and you can dynamically add more clients to that.
Correct.
So I was just about to suggest you that.
Okay, so yeah, see if you
It's not only about GlusterFS, okay. It's that we want to introduce a layer of abstraction between the actual storage frameworks. Okay, so I think that answers.
because we are looking at hybrid solution for failovers, and high availability might be cluster, and we might be still serving part of
From
say
our LMS
eBooks or something like that, from our current ZFS based mount. So you cannot have various different mount points on client applications, which is again prone to a lot of failures.
So the one more reason why there is a level of abstraction is for the lifecycle management as well.
And we want to introduce a layer of security to that, because it's assets that we are talking about. So it's a security layer that we want to put over there.
So what we are doing in the lab, we have configured Gluster